We're going to be taking a look at parabolas from a different perspective. And notice that chapter 10, section 2 above is called conic sections. So we're looking at parabolas, ellipses, hyperbolas, and really circles as well as a subset of the conic sections. So then the big question is, what the heck do you mean by conic section? Okay. So this is just a good overview of what we're talking about when we talk about conic sections. I don't think that you necessarily have to draw all of the pictures here, but just kind of listen, look, ask questions if you have them. Conic sections are defined as the cross sections of a double napped cone. And if you'll remember in geometry, you should have talked about cross sections when you were doing your three-dimensional shapes, prisms, cylinders, cones, things like that. A cross section is like when you cut a three-dimensional shape and then you open it up and you look at the two-dimensional shape that's at the cut. What is that shape? That's your cross section. So if I have a circular birthday cake, okay, it looks like a cylinder, and then I cut it to make a piece, and I look at the side of the piece, it would just look like a rectangle, even though it's a circle. Okay, so you're looking at the flat shape that's there from the cut. So we've got 4 different shapes. And a little hard to see here, but this shaded piece is the two-dimensional plane, kind of like our knife, which we're making the cut. And these are the different shapes that we can get. Now, it does say also double napped cone. So we're not just looking at a single cone. There are actually 2 cones when you think about conic sections. Some of the conic sections only work with one of the cones, so you can really imagine a single cone, but the hyperbola, notice, is crossing through both cones, so it has to have the double nap. So they meet at the vertex kind of stacked on top of each other there. So think about how the plane is changing so that you can get the different shaped cross sections. In order to get a perfect circle, what must be true about the plane that you cut the cone? It must be horizontal. Other ways to say that? What if my cone is tilted? It must be what to the base?
Right to the base of the parallel.
That other P word. It must be parallel to the base. But here, if we have it, upright cone, yeah, definitely horizontal. But it's got to be parallel to the base. And if you were to get closer to the base, your circle would have a larger radius, be larger. And if you get closer to the vertex of one of the cones, then the circle gets smaller. Okay. Now, the ellipse, which we kind of talked about in our last chapter, because we saw a round shape that looked like an oval. Okay. When we said this mathematical name would be an ellipse. The ellipse is formed if you go in one side of the cone and out the other side of the cone. So you're coming in at a side and out of the side, but it's not parallel to the base. It's not going to be perfectly round. So it's going to be an elliptical shape. Okay. Parabolas cut through a side of the cone, and then it comes out the base of the cone, and it doesn't ever cross the other cone at all. So when you're thinking about this parabola shape and the plane that makes the parabola, this plane must be parallel to the lateral side of the cone in order for it to not cross the other cone. If it's not parallel, then at some point it's going to cross the second cone, which would make 2 U shapes, which is the hyperbola. Now, something to note about these conic sections, in theory, when you're thinking about the double napped cone and we're thinking about these graphs, the cone would go on forever. Clearly it looks like I have a top and a bottom to my double napped cone, but in theory, the cone just extends out and out and out. So if you have a shape like a hyperbola or a parabola, when you make that U shape, those sides just keep extending, okay, either up or down or whatever they may be. Okay. So that's a side note there. And those are the 4 different conic sections. Now, below those 4, I have some that are called the degenerate conic sections, and they're like the ones that you could cut the cone different ways, but you wouldn't make a nice 2-dimensional shape. So if you cut it through the point where the vertices meet for the 2 cones, then you just get a point for your cross section. And so we're not really going to do a lot with that. If you cut it perpendicular to the base through the vertex, okay, you're going to get intersecting lines. And then if you cut it parallel to the lateral sides through the base, you're just going to get a single line. On that lateral side, there'd be infinitely many points that are tangent to that plane, and they would all lie on a line. Okay, so those are what we refer to as degenerates. Okay, not really shapes at all.
What's that first one?
A point? Well, I don't know. Do you mean degenerate or do you mean degenerate is what that says. Okay. So those are the conic sections. Now I'm going to ask you, and like this would be our like one short quick lesson about a circle. We're not really going to spend time going over notes for a circle. What is the geometric definition of a circle? Talk really quickly with your small groups. How could you define a circle from geometry? Go real quick, like 30 seconds.
The radius is
Every point on the line.
Do I have a volunteer who would be willing to share with me their thoughts on what is a circle? Okay, Mitchell, what did you guys say for a circle?
Sort of like all the sides are equidistant from the center at all points.
Yeah, the side is equidistant from the center at all points. So all points on the circle equidistant from the center. I love it. Okay, that's going to sound very similar to the geometric definition that we get for a parabola, but a little bit different, obviously, because they're different shapes. But I love that. Do you remember the equation for a circle? X squared plus y squared equals radius squared. So r squared. Right? We've seen that just last chapter, right? Okay, and I kind of talked about this Pythagorean theorem. This is the equation of a circle. Okay. What's special about all of those circles? X squared plus y squared equals r squared. They're all where? They're centered at the origin. Okay, they're all centered at the origin. So now I'm going to give you another like 20 to 30 seconds to talk to your group. Do you remember how to change that equation so they can have your center somewhere not the origin? Okay, so talk real quickly with your small groups. What does that equation look like so it's not at the origin?
makes sense. Like, you have x and then parentheses plus 2 squared when you side or side on the outside.
Okay, any ideas how we can get the equation to be not centered at the origin? Jordan, what did you guys say?
Said like the transformation, so if you had in parentheses x plus 2, or if you had on the outside plus something up or down.
Oh, transformations, like all the transformations we used to do. What, if she gave us an actual number, x plus 2 squared, does anybody remember what variable you would put in there with x? What letter? For transformation? H and k. So h goes with x and k goes with y. So the equation for a circle not at the center would be x minus h squared plus y minus k squared equals r squared. And so you would just pull out hk as my new center point, plot that point, and then figure out whatever your r value is, and then you could just count left, right, up, down, and draw a nice little circle. Okay. So you already know a lot about one of the conic sections, which is the circle, and basically that would be the equation that I would give you if we were to do a lesson on it. Okay. Remember that because in this equation you have x minus h squared and y minus k squared, when you pull them out of the equation, they both look like the opposite of what they really are. So where Jordan told us, like her example was something like the quantity x plus 2 squared, what would her h value have been? If it said x plus 2. Then h would have been a negative 2, right? You would have done x minus negative 2, which then turned into x plus 2. So it looks like the opposite. The same this time is true for k, which isn't normal with like a function when the plus k is just like out on the outside, but it says minus k. So if you had like y minus 5 squared, the k value is really 5. Okay, so a little note of that. They both look like the opposites. Go ahead and jot down the definition. I'm actually going to move everything so you can have a little bit of time. Jot down the definition to a parabola, and I'll try to make this a little bit bigger. Okay. If you want to draw a picture, you can. This is the geometric definition of a parabola. As you're jotting it down right now, it may not make a lot of sense. Write things down, then we'll talk about it, and you can kind of add to your notes as necessary. Okay, so as we go through the different conic sections in this chapter, it'll be section 10.2, 10.3, 10.4. Each one is a different conic. Each definition would start out with the phrase, a smooth curve graph. So Mitchell gave us that definition for a circle, a graph where all the points are equidistant from the center. We could add to that a smooth curve graph in which all the points on the graph are equidistant from the center point. So definition of a parabola, a smooth curve graph in which every point is simultaneously, which means at the same time, equidistant to the focus as it is to the directrix. So think about that definition and how similar it is to really Mitchell's definition of a circle, right? The circle, all the points had to be equidistant to the center point. The big difference here with a parabola is the points on the parabola need to be equidistant to not one thing, but two things. So they have to be the same distance from the focus as they are to the directrix, and the other difference is that distance does not always stay the same. Okay, so as you move around the parabola, that distance could increase. You get further, but it's the same for the focus as it is to the directrix. So focus and directrix are like two new vocabulary words. Basically what I want you to think about the phrase focus and directrix is these are parts of the parabola, just like a center point is part of a circle, even though it's not on the circle. So when we graph with conic sections, we specifically want to see the focus point and we want to see the directrix. Before, we've never really seen that with a parabola. Okay, we've just graphed it as a function of x and y. Okay, so a focus is a point that lies on the axis of symmetry. So notice in my picture, I've got a red parabola. We already know that that point that is the minimum or maximum value is called the vertex. There is a vertical line passing through the vertex, which represents my axis of symmetry here. Okay, and the focus lies somewhere on the axis of symmetry. Now, the thing to remember about the focus is the focus should be inside the parabola. Think about it, I always say, like, think about somebody doing a trick out in the hallway, some kind of like stupid human trick that you might see on a late show. Okay, and everybody wants to see the stupid trick. So they're all going to crowd around that person so they can watch what's happening. Okay, so the parabola opens around the focus point. Okay. The directrix is a line that's perpendicular to the axis of symmetry, and it always sits behind the vertex. So it sits behind the U-shaped graph. And the parabola never ever crosses the directrix. Okay, so it has to be behind the vertex point. Okay. So these two items right here are not on the parabola. Okay, that's important to remember. Really, only point we currently have located on the parabola is the vertex point. That's actually on the parabola. The other things we're talking about are around the parabola. Okay. And then the blue lines, the solid blue lines here, are trying to illustrate this phrase that they have to be simultaneously equidistant to the focus and the directrix if you're a point on the parabola. So if I'm this point right here, okay, I'm on my red parabola, so I'm a point on the parabola. If I measure the distance to the focus and I measure the distance to the directrix, those two distances should be the same value. So in geometry, I could mark those with like that congruence tick mark. If I pick a different point somewhere else on the parabola, suppose I pick this point up here, if I measure to the focus and I measure to the directrix, then these two are congruent to each other. They may be longer than my previous distance, but these two are always the same. Okay, so that's the geometric definition of the parabola. That geometric definition is what makes the parabola useful in a lot of real-life applications. So you probably use parabolas every single day on your drive to school. Headlights on a car, parabolic shaped. So around the bulb, you've got a parabola. You light the bulb. The light goes out to the parabolic shape, and then it reflects back to the focus, creating the stream of light. Okay. Satellite dishes, flashlights, like those are going to be some really common instances where we see parabolas in our real lives. And it's the geometric part of that that makes it really useful. Does anybody have any questions about the definition that you want to ask me, or the picture is not clear? Okay. These are the equations of the parabola, and this is where we're going to put most of our focus. Like the geometric definition, I want you to know what it means. I want you to know how it could be used in real life. But of course, we're now going to look at it from the equation perspective. So we've got two equations for parabolas. I'll let you jot those down. One is the quantity x minus h squared equals 4p times the quantity y minus k. And the other is quantity y minus k squared equals 4p times quantity x minus h. And this is unlike any equation for the parabola that we've seen before. So these are brand new equations used solely in the conic section. Notice there are some similarities there to the circle equation that you guys gave me from geometry, mainly that like idea of x minus h and y minus k. So hk is going to represent something for us on the parabola. Main difference for a parabola is hk gives us not a center point, but the vertex of our parabola. Okay, so let's write that down. for both of these equations, I'm going to put it in the middle because this applies to both. HK is my vertex. Okay, it's a point on my parabola. It is my min or max point if the parabola opens up or down. It'll be like my most left or most right point if my parabola opens left or right. Okay. In these two equations, in addition to h and k, we have this p value, which we've never seen before. So I'll tell you right now, p is the distance from the vertex to the focus. So P is going to represent the distance from the vertex to the focus. And because the vertex is a point on the parabola, and all points on the parabola need to be simultaneously equidistant from the focus as they are to the directrix, then P can also represent the distance from the vertex to the directrix. Now, those would be going in opposite directions. One's going inside the parabola and one's going outside the parabola. Okay. Which equation, x minus h squared or y minus k squared, looks most like the equations that you've worked with before for a parabola? Heard a soft voice.
Using K squared.
Why? What are some other equations for a parabola that you've worked with? X squared. Probably remember from like parent graphs, y equals x squared. We also have like our old standard form from Algebra 2 or our new standard form from first semester pre-calc. Which one does this look most like? The x minus h squared or the y minus k squared? What do you think, Trey? Do those equations look most like x minus h squared or y minus k squared? Yes, they look most like x minus h squared because what thing will be squared? The x, right? Even if I expand this, the x is going to be the thing that's squared. So these are the parabolas we've always worked with. They're parabolas that open up or down. Okay, so when you have something that looks like x minus h squared, you know that the parabola is going to be opening up or down. It will open up if you have a positive p. It will open down if you have a negative p. So you can kind of keep that in mind as you're graphing. What direction should my parabola open? Which means that y squareds are going to open right and left. Okay, so these are going to be right and left parabolas. Negative p will be to the left, positive p will be to the right. And that's going to allow us to help us find the focus and the directrix for each of them. Okay, so I'm going to focus on the x squareds right now. I'm going to add here, what's my focus, what's my directrix? Remember that the focus is a point that should lie on the axis of symmetry. If my vertex point for this parabola is at hk, then my axis of symmetry is x equals h. And so to get to my point P, I'm either going to be going up or down P, depending on the direction that it opens. So my focus point is going to be h comma k plus P. If the parabola opens up or down, then the directrix must be horizontal. Okay, so I'm going to put that down here. And if it's horizontal, it's always of the equation y equals And we'd be focused on our k value. We'd go in the opposite direction, so it's going to be k minus p. On the other equation, x and y have switched. Now we're opening right and left. So that means instead of adding and subtracting the p from the k, we're going to be adding and subtracting the p from h. So my new focus will be h plus p, comma k. And my new directrix, because x and y have switched, will now be a vertical line, which will be x equals h minus p. Now, I would write these things down. I would maybe review them in my notes. I would try to make connections for these two things, but I'm going to be real honest right now and say that when you do your homework or your examples, most students who have the greatest success are not going to memorize those things. They're going to plot their vertex, and they're going to count with P, and then name that point after they move it. Count with P and name that line after they move it. Okay. But you'll be able to make some connections here that these things are always true. Okay, so let's do an example where we can graph a parabola. We're going to start with this example right here. X minus 3 squared plus 8 times y minus 5 equals 0. So one thing I would say to you at the very beginning, identify which equation it looks the most like. So I'm looking for, is it x squared or y squared? This one's x squared. So I want it to look like the equation we just wrote down. X minus h squared equals 4p times y minus k. This equation does not look exactly like that right now. I need to move the 4 or the 8 times y minus 5 to the other side. So I'm just going to subtract that term. So it would be x minus 3 squared equals 8, negative 8 times y minus 5. You okay with that? After I do that, then I can find everything I need to be able to graph my parabola. What is my vertex point? Turn to the person right next to you and share with them what you think the vertex is. Allie, what's the vertex?
3, 5.
3, 5. Notice both of them look like minus, but then they're both positive when we pull them out of the equation. Also, find the value of P, because then I'm just going to, from my vertex, I'm just going to count P to my focus and count P to my directrix. So turn to the people around you and tell them what you think P is. P is equal to? Kirsten, what do you guys say P is equal to?
Negative 2.
Negative 2. How did you get P is negative 2? I don't see negative 2 anywhere.
Well, in the equation it's 4p, and you have negative 8.
4P is equal to negative 8. Multiply by 1/4, divide by 4, P is equal to negative. Okay, so if you need to solve it algebraically to get your P, you can set up a little equation. 4P is equal to that number. Okay, so here's what I'm saying I would do next. I'd plot these two things, and then I'd name my focus and my directrix. So I'm just going to put focus, directrix, but I'm not going to memorize that stuff I wrote on the last slide. I'm just going to like think about it on my graph. Okay. So I'm going to plot 3, 5. That's my vertex. I'm going to go ahead and label it with a V so I remember. This parabola opens in what direction? It's an x minus h squared, so it opens up or down. Because p was a negative, then I know my graph opens down. So in order for my graph to open down, my focus must be going down. My p-value is -2. So from my vertex, I'm going to count 2 down. There's my focus. Could you tell me what the ordered pair for that focus is? 3, 3. Thank you for whispering. So I'm just looking at the graph. If I was at 3, 5 and I went down 2, then I'm at 3, 3. And to get my directrix, instead of going down 2, I'd want to go up 2, because it's going to sit behind my vertex. And you can put a point there, but remember the directrix is not a point. The directrix is a line, a horizontal line. So we're going to draw it as a horizontal line. And what would be the equation there? Y equals 7. Because if I was at 5 and I went up 2, then I'm at 7. So to me, it's a lot easier to figure out where my points and directrix are if I'm just leaving it on the graph and counting. Now, you could have some like later on where you'll be like adding radicals. So to give an exact value, you'd say something like 6 plus square root 2. Okay, so like that would be okay. You could have fractions here in parabolas, so you might have to add or subtract a fraction. Fine. Okay, not a big deal. You could do it. The last thing we want to do is like make our parabola open down. I'm going to ask you to get 1 or 2 other points for the parabola. And the way to do this is we are going to basically find the matching point for a point that is, count this, 1, 2, 3, 4 units away from the directrix. So we're going to go to our focus, and we're going to go 1, 2, 3, 4 units away from the focus. And we're going to plot a point right there. Because then this point on the parabola is 4 units away from the focus, and it's 4 units away from the directrix. Okay. And I could also count 4 in the other direction and put a point over there, and that will help me make my parabola. Now, the trick or the shortcut for this is, that's 2 times p. Your p-value is -2, so -4, but you could go left 4 and you could go right 4 from your focus, and that'll get you your other points for your parabola. But then if you always count back to the directrix right there, it'll be the same number, 2p. So maybe you could go back to your notes on the previous one, and you could add something down here that says, like, to get an extra point, count 2p from focus. And so you remember how you got that. To get that extra point, count 2p. And you can go in both directions. You can go right and left. If you needed to have one that opened left or right, then you would count up or down, 2p. Okay, does anybody have any questions about the method that I used for graphing the parabola? Okay, we probably don't have time for both of our other examples, so I'm not going to work out this example. I just want you to look at it real quick. X equals -1/2 y squared. What are some things that you know about this parabola instantly? Where's its vertex? HK. 0, 0. It's at the origin. Okay, so vertex could be at the origin. That's fine. What direction does it open? It opens left. Because it's y squared, it opens right or left. Because it's negative, it will open left. And if you were gonna solve for p, be very careful here. You want your y squared to be all by itself. So that would be like negative 2x equals y squared. And then you would solve for p from there. Right? P needs to be on the side with the variable that's not squared. So then you could say 4p equals negative 2. Therefore, p equals negative 1/2. Could you count 1/2 on the coordinate plane? Yes. 1/2 away from the origin, right and left. That'll get you your focus and your directrix. Okay. Okay. The other one that I want to show you is this one here. So I would write this down in your notes. X squared minus 6x plus 4y plus 13 equals 0. And this is in what we call not a standard form, but a general form. It's just got a bunch of terms. It doesn't have those parentheses that I'm looking for. Okay. And if I were to look at this one, I'd say it looks most like x minus h squared equals 4p times y minus k, because I can see that x is squared. So I can identify it that way. But I need to make it look like that group of parentheses. And the issue here is I have an x squared and a minus 6x. So that means I'm going to need to complete the square. Complete the square, coming back at it. So here's what I would do. I would get x's on one side, so I'm going to have x squared minus 6x. I'm going to leave some room to complete my square. Equals, I'm going to move the other terms to the other side, negative 4y minus 13. So I'd have to subtract them both. What value completes the square for x squared minus 6x? How did you get that? How did you get that? You can take half of the middle term and square it. But yeah, you're looking for something that will factor so that it has the same two factors. Okay. So if I add 9 on that side, then I need to add 9 on the other side. This left side would be x minus 3 times x minus 3. That's what Nick's talking about. They add to negative 6, but they multiply to make 9. So that's x minus 3 squared. Oh, see, look, I got it like my x minus h. Cool. And then on this side, it would be, this stuff will come out to be negative 4y minus 4. You never want to have a coefficient for y, so whatever is in front of y, factor it out. So I'd have to factor out a negative 4. This one works out nicely. It'll be y plus 1. It doesn't have to be a nice number there. You could have a fraction for your vertex. Okay. But now you can go through and you can do the same stuff we did on the previous one. Since this is x squared and it's negative, we know it opens down. We know the center point is at 3, negative 1. We know that the p-value is negative 1. And we could count in both directions. You'll have a homework assignment. It's on your gold sheet. Please work on that over the weekend. I would say do it tonight so you can have it out of the way.